Hello, my name is Christina, and this is my entry for the video assignment showing the different potentials of a neuron cell, which are the resting potential, the local or gated potential, and action potential. So first off here, to start with, we have my illustration of a neuron cell, which you can see here of the cell body, the dendrites, and the axon over there. And this neuron gets its information from its dendrites and cell body, and is also connected to other neurons. Like, think of a network or a spider web. And based on all that information, neurotransmitters, it could fire an action potential down the axon or not. And we'll talk a little more about that later. So now let's talk about the different potentials. So resting potential, really the potential of a neuron relative to its surrounding when it's stimulated or involved in passage of an impulse, while local potential is based on the stimulus that neuron is getting, basically from another neuron connecting to this neuron, like on its cell body or through the dendrites, and then there's going to be neurotransmitters, and that will create a change in its charge, whether it will hit that threshold or not, and whether that will create a action potential or not. While action potential can lead to synaptic activity, it is actually a brief renewal of electrical polarization of the membrane of a nerve cell. When I say brief, it's only like 1,000th of a second change in electrical polarization. And remember that only nerve cells and muscle cells have action potential. And so what is potential? Potential is separation of charge and potential to do work. So let me show you exactly what that is. So here, these are, as you can probably tell, these are axons, and in between those axons, the neuron, right? So the cross section of that neuron, when I say separation of charge, is the inside is negative and the outside is positive. So a neuron has a net charge of negative 70 millivolts at rest. But remember that rest doesn't mean there's nothing going on in there. So let's look at resting potential. The membrane is a salty banana is the best analogy I could find. Banana has a lot of potassium. So on the inside, there's a lot of potassium here, as you can see, and a little on the outside. Also, we have anions, which are negatively charged, like the protein here, like this one. This represents a protein inside, and it's negatively charged. And when you want something salty, you put salt on it. So here on the outside, you have chloride and sodium ions. And some of this will seep through the membrane, like when you put salt in a banana, the inside will get a little bit salty. So some of those sodium and chloride ions will be inside the membrane. Just want to point out that in this state, there is no potential there. So due to permeability of a membrane right here, right? Membranes are permeable, as we learned, it's hydrophilic, and it's permeable. So because of that permeability, there are leak channels, or it's just an opening. I would think of it as just an opening which allows different ions to come in or go out. For example, the potassium channel right here. You can see this channel allows potassium ions to move out, because if you have a higher concentration of potassium ions on the inside, it will go out of the membrane through that leak channel because of the electrochemical gradient. Just remember diffusion. In diffusion, the ions or solutions will go from area with higher concentration to lower concentration. So basically that's what's happening right here. So potassium ions, because there's a lot of them on the inside, it will go out, while sodium channel does the opposite. Because there's more of them outside, its electrochemical gradient is going inward. So a lot of the in this let's go back to the previous illustration I showed you. So a lot of the sodium ions outside will go inside because of diffusion, basically, and permeability of the cell membrane. If sodium ion and potassium ion will just keep doing this, it will just keep going out and inside. The potassium will go outside, and sodium ions will go inside. Then so soon there won't be any potential, because it will just balance out. this is where the sodium and potassium pump comes in, right here. With the use of ATP, so ATP is involved in this pump right here, it will drive 3 sodium ions out per 2 potassium ions in. And it is our, I would like to think of it as a membrane's check and balance counter, with the sodium and potassium channel doing what they do, and the sodium potassium fact checking them, and a different electrochemical gradient putting a difference in charges, arresting potential with negative millivolts charge. These all could lead to action potential. So now let's move on to action potential. So action potential. Remember that action potential can lead to synaptic activity, and the main players in action potential are what we call voltage gated channels. So what we have here is an example of sodium voltage gated channel and a potassium gated channel. This is the one we were discussing earlier, just a leak channel for sodium and potassium. So anyway, the main principle is this channel opens when it approaches a certain millivolts of charge. So what happens is, for example, we look at the sodium voltage gated channel right here. It has a polypeptide right here as a tail. Its millivolts thresholds is negative 55 millivolts for it to open, and when it does open, like it goes like this, right? It opens like that. So this thing goes like it opens. So a surge of sodium ions go in. So there's gonna be more sodium ions inside, and the surge of sodium ions going inside until it reaches 30 millivolts and it closes, and then the potassium voltage gated channel opens and a rush of potassium ions rush out. So this opens and the potassium ions, they rush out, which then causes a repolarization. So the inside of the membrane, the cell membrane, becomes more negative because a lot of the positively charged potassium ions is going out. That is what we call repolarization. It takes a while, but it does close, but it undershoots the negative 70 millivolts that's required for the sodium ions to close again. Erase that. So it undershoots the negative 70 millivolts, but will be balanced out by those leak channels right here we talked about earlier. So as these two opens and close because of the polarization and repolarization of the inside and outside of the cellular membrane, these sodium leak channels and potassium leak channels continue to work. So what does the opening and closing of the potassium voltage gated channel and the sodium voltage gated channel opening and closing and rushing in of the sodium ions and gushing out of the potassium ion, what does it mean for the neuron cell? So over here at this point right here, which is called the axon hillock, here the sodium gated channel opens up, and then there's going to be an influx of, as I showed you earlier, there's going to be an influx of sodium ions inside, which repel each other. So this one goes right here because they're both positively charged, and as what we learned, positively charged things in general repel each other. And this one goes right here, this one goes over there. Then this will change the voltage or cause, this will change the voltage of the next axon over here. And then it will change the voltage, hit the threshold of the next segment, opens it up, and so on until it reaches the end of the axon. So we've discussed resting potential and how that may lead to action potential. But what is local potential? When we say local potential, it means the potential might go towards or away from that threshold we talked about. And you can see that in the book. It's like this spike thing. I think it's on page 443 in our book. And this is influenced by other neurons connected through synapses, which we discussed previously in our previous before this discussion. And over here, as you can see, these neurotransmitters are released across the synapse, and it opens a chemically gated channel, which this is representative of the chemical gated channel. These neurotransmitters, you can see right there, will dock on the postsynaptic side of that receptor over here on the side of the cell, neuron cell, and will open this chemical gated channel. And what the opening leads to action potential or not depends on what type of neurotransmitter and receptor it is. Is it excitatory that moves towards that threshold that could lead or not, that could lead to action potential, or is it inhibitory sorry, I can't speak, which moves away from that threshold we talked about. A great analogy I came upon on YouTube is actually by Bozeman Science. We can think of a neuron as having an analog side and a digital side. On the digital side, the action potential, which is like all or nothing. You can compare it to a computer language, which is composed of ones and zeros. As in computer languages, it's a completely different course, but you can think of it like that, digital. While on the analog side, where the dendrites and the cell body is, information comes from a lot of other neurons. A lot of neurons will attach to these dendrites or the cell body itself, and will release neurotransmitters, which could be excitatory or inhibitory, as what I've explained earlier. And the summation of all those signals tells that neuron to either fire action potential when it hits 55 millivolts or not. That is the all or none law. So to summarize, resting potential is negative 70 millivolts. The neuron is sitting, has potential to do work like a battery, established by permeability of the membrane and the sodium and potassium pump we talked about earlier, right here, the sodium and potassium leak channels and the sodium and potassium pump. While graded potential is based on all the neurotransmitter that's connected to that neuron, and actually it's this one. Yeah, this one. So graded potential is based on all the neurotransmitters that's connected to that neuron, and if we hit that negative 55, this one, if we hit that negative 55 millivolts, the sodium and potassium chemical gated channel opens, resulting in all or none action potential that runs through the neuron. It will run through the neuron to the axon and then will cause movement. And basically that's it. And there's a great link that I came about. It's this one right here. If you can see, it's actually PHET. So phet.colorado.edu/en/simulation/neuron. It shows this great simulation of the different channels: the potassium channel, the sodium channel, the chemically gated channel or the ligand activated channel, and the sodium potassium pump. And it shows how these all plays out and how they all play together or work together to do work, basically. So thank you for watching, and I hope you learned something.